Hi everyone, it's time for another homework tutorial. Unit 3, we're going to be covering Chapter 7, some problems in Chapter 7, which is about risk assessment. And then Chapter 8, time value of money, one of my favorites. Let's jump to Excel. Okay, so there's a lot of problems here. I won't deny it, but a lot of them will be very, very easy to do in Excel. So don't be too intimidated, and I'm going to give you some examples for every one of them. And there's only one that you're going to do totally on your own, 7, 15, and 16, but we're going to do one right here that's pretty much exactly that. You will be prepared. Okay, so let's start with 7.2. And here's in the book on page 158, it says, Milk U, an agricultural consulting firm, has developed the following income statement forecast. And that's what we're given that right here. And it wants us to calculate the expected value of Milk U's operating income first of all. So let's do that. And the nice thing about these problem templates, the book gave us these, it gives us the formulas we need, so we just need to plug that in and apply it. So EBIT times the probability, which is right here. So that's just going to be some cell reference math. Do it for that top row and then fill it down. So I have the expected value for each operating income times its probability. So that's part A. And then the sum of those, and we can actually do an alt equals, sum that. There we go. So that's what we needed in part A, nothing to it. Expected value of the operating income. It's just the sum of the probability weighted possible EBITs. Calculate the standard deviation of Milk U's operating income. Alright, that's a little bit trickier. That's a 3-step process here. So we have to take the EBIT and subtract the mean. So we'll do that here. Then we have to square that result there. And then we have to multiply those by the probability there. And then we can square all that to get the variance and then take the square root of that. So kind of complicated, but not too difficult because, as always, Excel does the math. So EBIT minus the mean. Now, notice what happens here. Here's a little Excel skill for you. If I keep that mean as just F20 and fill down, it's going to move down to F21 and then F22 as I fill the cell down. So what I want to do is lock in the row component of that, $$20, and then if I fill down, it's going to move the EBIT value down 1 every time. So here I'm D16, but I'm still in F20 for the mean value. And at the very bottom one here, you'll notice same thing. I'm in the bottom row, the final EBIT value, but I'm still in F20 for the mean value. So use that $sign to lock your cell reference. Otherwise, you're not going to get this right. Okay, now we're going to take that value and square it. So that's just, again, cell reference. Exponent is the caret shift 6, and then the second power. And we'll fill these down as well. Okay, now multiply those times their probabilities. The probabilities are still back here in column E. And then we can fill that down. All right. So doing all these operations on that whole array of 5 values, it wasn't too difficult. And now we can do the sum of all of these, which is the variance. So we're going to have to do equal sum here and then select that range. So now we have the variance, and then we can take the square root, which is a function sqrt of that value, and that is our standard deviation of expected incomes, $122. So a lot of math there, but it actually wasn't that hard, especially with this pre-built framework. Okay, then C says calculate the coefficient of variation of Milk U's operating income. The coefficient of variation, they give you the formula right in here, standard deviation divided by the mean. So that equals the standard deviation here divided by the mean, which is still sitting up there in F20. So there we go, 34.9% is my coefficient of variation. That tells me how spread out my expected operating incomes are. Okay, now in part D, it says recalculate the expected value, standard deviation, coefficient of variation for Milk U's operating income if the company's sales forecast changed as follows. And what we've done is just changed our probabilities. Our expected sales volumes are the same. All we've done is change the probabilities. So it's going to be the same math. Now, let me show you a sick little Excel trick. If I select all of this, including this, and including these, I'm holding Control down to select all of that, and then Control C, Oh, we can't. Okay, we have to do one chunk at a time. Okay, so Control C, Control V. It's going to apply the exact same math. It's just going to shift it down however many rows we copied it down. So all I have to do is cut and paste. Pretty cool, huh? Okay, and I'm just verifying that that's doing the proper thing every time. There it is. And then I can just take the sum again, auto sum, alt equals the rows above, and then copy these formulas right down here. It's going to shift all the references down for me, and I'm done. And now all it's asking us to do is comment on MilQ's change in business risk. Well, the square root, or the standard deviation, went up, and the coefficient of variation went up. And what caused that? That was caused by basically what we would call a fatter tailed distribution. It's more likely that we're going to have the very low or the very high volume of sales. Those probabilities went from 2% to 10%, and of course that drove the coefficient of variation up. So it's a higher risk scenario because there's more likelihood of the very low or very high results. So there's kind of a hands-on feel. So you can type in, think that through, type it in your own words down there. But there's a hands-on application of these important concepts of risk measurement, standard deviation, and coefficient of variation. Now, 7.4 is a very similar problem, and then we've got two companies, Equity Eddy and Barry Borrower. We're going to basically do the same calculations and then compare their financial risk, which is the difference in risk based on adding debt to the operation. Of course, Barry Borrower is going to add debt to his operation. Equity Eddy is not. So it wants us to calculate expected values of their net incomes. Okay, same thing here. Net income times its probability. We've got a probability distribution. I'll do it for Equity Eddy, and I'll let you complete the problem for Barry Borrower. We want to add those, and we're going to subtract the mean here. Now I'll show you another trick. We could use a locked reference, which is the $sign in front of the row value. We could also name that. We could just name that mean up here in the naming box, and watch this. I can do equals net income minus the mean. I type it in, and that mean value will stay the same each time. Now note, if you're going to copy this whole thing down here, you'll want to name this one down here for Barry Borrower a different name, and then change the name in here. Otherwise it'll go back and grab that mean, and you'll be wrong. So make sure you make that change if you're going to use a range name. Net income minus mean squared, so we just take this value and square it, fill it, and then multiply that squared value times the appropriate probability in the same row. Whoops. Times the probability. There we go. Fill that. Okay, then the sum of those probability weighted squared differences between net income and the mean, it's a lot to say, is the variance. The square root of the variance is the standard deviation, and the coefficient of variation is the standard deviation divided by the mean. There we go. That should be a percent. Okay, so there's the procedure for calculating all of that. Do the same thing for Barry Borrower and see what the difference is in the coefficient of variation based on the fact that Barry Borrower is adding some interest expense. He's borrowing. Okay, and then you can comment on the differences between their coefficients of variation down here. Okay, now 7, 15, and 16. Basically the same exact procedure. So I'm going to let you run those on your own. Okay, for this one company, and what we're going to do is have it with no fixed expenses over here, so you'll have to enter zeros. I think that's right for 715. Let me check. Yeah, no fixed expense, so you just fill zeros in here, and then the calculating operating income is going to be sales minus variable expenses. You'll just do that with cell reference, equals sales minus expenses. Okay, fill that down. And then over here for the other company, we've got some fixed expenses filled in. So the operating income estimate is going to be sales minus variable expenses minus fixed expenses. Like so. Fill that down, and then do the same calculations for standard deviation, coefficient of variation as we just did. Okay, so that wraps it for chapter 7 problems. We weren't too heavy on that chapter. We're going to be a little more heavy on chapter 8. But the good news here is this is very familiar stuff, for me especially, and very fun. I really enjoy doing time value problems. So, and also a nice thing about time value problems in Excel is that there's a very fixed procedure. There's a very fixed sequence of arguments in the Excel functions. And that goes in this order: rate, INPER, payment, PV, type. Okay. Now some of these things will not be kind of flopped around depending on what we're calculating, but just kind of remember that sequence: rate, INPER, payment, PV, type. Those are all the arguments we need in our present value or future value functions, our time value functions. So what Excel's doing here is that present value, future value math, FV, you'll recall, is our payment or present value, our amount of money, times 1 plus R, the interest rate, to the n. That's the basic present value equation. Of course, it's a summation if we're talking about annuities or repeated sums. And then present value unwinds that, remember, by taking the future value and dividing it by 1 plus R to the n. So in both cases, we have rate, n for INPER, number of periods, that's n, R, n. Now payment, if we're working with annuities, and here we're not, here I'm just working with a lump sum, a present lump sum, a future lump sum. But if we have annuities, we're going to do the summation type formula with payment. Okay, so that's what PMT is for, payment. Payment, PMT, rate, INPER, payment. And then whether we're doing PV or FV, we fill in the opposite one if it applies. Sometimes it doesn't. Sometimes we assume that there's not going to be any value left at the end or at the beginning. So those are in brackets to indicate that they're optional. PV slash FV, depending on which one we're using. And then type is also optional. It defaults, I think it defaults to 0, which is end of period. Okay, that can be 0 or 1 for the payment occurring at the end or beginning of the period, and that alters how long we're discounting it or compounding it for. Typically 0 is the default, so if you leave it blank, it goes with that. So rate, INPER, payment, PV, FE, type. That's the sequence of arguments in any time value function in Excel. So with that in mind, let's jump in here. And you'll notice I've grouped a lot of these, and I'll do one, and then I'll leave exactly similar one for you to do on your own. So 8.2 and 8.4 are very similar. So let me show you how we're going to do 8.2. Page 197, it says calculate the future value of $20,000 10 years from now if the annual interest rate is. It gives us a lot of different options, so I'll show you how we're going to do this. First off, 0% for A, and let's make sure we format that right. Number of periods 10 years from now. It says $20,000 10 years from now, so that's a present value. Put that in as 20,000. We can format it as dollars if we want. There's no payment. It just says the future value of $20,000. No recurring payment over that 10-year period. So we're going to go ahead and plug in 0 for the payment in that situation, and we'll go ahead with 0 for the type argument. Now equals FV is a future value calculation, and I'm just going to plug in, working down my table here, my arguments for rate, INPER, payment, PV, and type, and bada boom, I'm done. And if I want that to be positive, I can simply change the payment to negative. Okay, so there's A, 0%. Now to do the other options, watch how easy this is. Control C, Control V, and what we did in option B was change the rate to 2%. It's going to automatically recalculate everything. Of course, the future value goes up. Now notice here the future value doesn't go up because there's no growth, right? But here it goes up by compounded 2% because there's growth. And we'll copy this again and paste it again. Control C, Control V, and change the rate to 5%. And of course, we're going to get a lot more growth. Now we're up to 32,000. And then copy it again. Control C, paste it again. Control V. This one's part D. And we've changed the rate now to 10%. And of course, we're going to get a significant amount of growth. More than a doubling, right? Remember your rule of 70. 70 divided by R equals years to double. Well, 70 divided by 10 is 7 years, and we've got 10 years here, so that's going to more than double, and indeed it does. It goes from 20,000 to 52,000. Okay, so similar type of problem for 8-4, and you can do the same thing there. Enter your rate, all your arguments, calculate it here, then copy, paste, copy, paste, copy, paste, change the one argument you need to change, and you can see how that growth of the invested sum changes depending on the rate. Alright, likewise, moving right along, and now we're doing present value instead of future value. So we're going to work here 8 through 8, 8, 10, 12, 13, 15. I'll do a few of these and then leave the other ones for you to try on your own. 8, page 198, it says calculate the present value of 15,000. Let's go ahead and plug that in. That's going to be our future value now, 15,000. Let's make that money. To be received 20 years from now, that's going to be our INPER, right? At an annual discount rate, and then again it's going to give us 0, 5, 10, and 20, so we'll do the same thing, we'll copy down. So, and now we have no payment. It's just a lump sum. The present value of $15,000, so no payment. Type, we'll go ahead with 0 again. And our function is going to be equals PV. Plug in the values again with cell reference rate, INPER, payment, FV, type, and let Excel do all the hard work for you. Oh, now what happens if there's all these hashtags? That means our column's not wide enough. We just need to click and drag that over a little bit. And of course, there's not going to be a change in present value because there's no discount rate applied. Let's make that negative to make this positive. Okay. And again, we'll label this A, and then B, copy, paste, change the discount rate. It says 5%. And we're discounting, so the present value in 20 years is going to be significantly lower. Remember, the present value is saying what sum invested now at this rate would grow to this sum in 20 years at compound growth. Well, it turns out it's a substantially reduced sum, substantially discounted sum. Let's do the same thing again. Copy it, paste it again, and now plug in 10% for our discount rate. And that value is going to be even smaller, $2,200. And let's do it one more time for D. And here we're going to use 20%. This is going to take away almost all the value. You know, in 20 years, something growing at 20% is going to grow a lot. So it's going to take a relatively small sum invested today at that rate to equal 15,000. And look, it's only 400 bucks. Okay, so the higher the rate, the bigger the discount. Remember the Bocephus principle. If interest rates goes up, current asset values go down. That's what discounting is all about. All right, I'll let you do 8-10 on your own. It's exactly analogous to 8-8. I'll let you do 8-12 on your own. It's exactly analogous to those as well. Let's see. Let me do 8-13 for you because that one's an annuity. So what does that mean? The difference is we're going to have a payment argument. So this one says, what is the present value of a $2,000 10-year ordinary annuity at a 4% annual discount rate? 4%, so 0.04, format that. Number of periods, let's see, 10-year ordinary annuity. Payment, it's a $2,000 annuity. That means $2,000 per year. That's what annuity means, per year. So there's no future value now, there's just a payment, because at the end of an annuity it ceases, it doesn't pay you anything at the end, it doesn't pay you in lump sum. Ordinary annuity pays at the end. Now annuities can pay at the beginning, in that case they're called annuity due, and in that case we would use the 1 assumption there, but in this case an ordinary annuity it's going to be a type of 0. So to calculate that, now we just run the PV function with these arguments. There's our rate, there's our INPER, there's our payment, there's our FV, and our type, and that annuity is worth $16,000. That's what you ought to pay for it if that's the rate you think that is appropriate. Okay, and again, if you want that to be positive, you can just change the payment to a negative, to a payout. Okay, 8-15 is the same question, just with some different assumptions. So again, I'll let you run that one on your own. Okay, so moving ahead, 28, 29, 31, 32. We're going to do some solve for the rate or calculate for a perpetuity. So with these, I'll do one each as an example, let you do the other one yourself. 828, it says you invested $50,000, and 10 years later, the value of your investment has grown to $185,361.07. What is your compounded annual rate of return over this period? Oh my goodness, that sounds complicated algebraically, but using the same exact template, and then lo and behold, we have a rate function now instead of a present value or future value function. We can calculate this easily using Excel. So 10 years is my INPER. My payment is nothing because there's no payment there. There's just an initial amount I invested, which was $50,000, and then it grew to $185,361.07. Let me format both of those as money. Type. Let's just go with 0. When in doubt, go with 0. And then Excel likes us to have a starting point. I'll just put in 5% as a starting point guess for the interest rate. And then I'm going to run the equals rate function. And notice the sequence of arguments is the same. It's going to skip rate, and it's going to ask us for both PV and FV. So the INPER is 10. The payment is nothing. It's just a lump sum, not an annuity. The present value is 50,000 there. The future value is 185,000 there. The type is that. And there's our guess. And I think my problem here is that Excel needs PV to be negative. There we go. Yep, I just needed one of these to be negative, and lo and behold, I got my rate calculation of 14.0%. Right? So do the same procedure there on 829, and you can solve that yourself. They throw a monkey wrench at you there because the value of the investment falls. What does that mean? Well, what's the rate of return going to be if your value went down? It's going to be negative, right? And sure, Excel will calculate that for you. Okay, perpetuity. I've plugged in the perpetuity formula for us here. Perpetuity formula is PV equals just payment over rate. So we'll do this two ways. We'll just do the math for that, and then I'll verify with you doing that original process that indeed works. So let's see. 831 says, what is the present value of a $50 annual perpetual annuity or perpetuity using a discount rate of 2%? So $50 going on forever, perpetual annuity, perpetuity, at a 2% discount rate. Well, here I'm just going to use the math. Payment divided by rate, $2,500. Now let's check and see that the original procedure works. Rate 0.02, number of periods. Now for perpetuity, what's the number? Well, let's just put an arbitrarily large number of periods, like 1,000 years, and the present value is going to get vanishingly close here to the perpetuity function. In fact, that's what the perpetuity formula is. It's just a limit scenario of the present value math. The payment is 50 per year. The future value is none. The type is 0. Let's make that percentage and make this dollars. And then we'll run PV on that rate. An arbitrarily huge number of time periods is payment. This future value, this type. I forgot a closing parenthesis, and so we have it, 2,500. Now again, if I make my payment negative, Excel will make my present value positive. Notice, I mean, man, it didn't just get vanishingly close. It got pretty much identical. I'd have to throw in several decimals before we found that that's just a little tiny bit different than what the perpetuity formula gives us. All right, so 832 is a almost identical problem. So you can go ahead and run that. Do both, just to see how those two procedures relate. All right, we're chugging right along here. 845 and 853. Now we're looking at future value of annuities. 845, it's a two-parter. It's still pretty easy. It says it is the beginning of the quarter, and you intend to invest $750 into your retirement fund at the end of every quarter for the next 30 years. You were promised an annual interest rate of 8% compounded quarterly. Oh, they're going to throw a little monkey wrench in with this quarterly compounding, but we can handle that. In fact, I'll show you. We'll do this kind of a simplistic way, and then we'll copy the whole thing again and do it the precise way. So The simplistic way would be, it says how much will you have after 30 years upon your retirement? Well, let's just go ahead and run this annually. $750 per quarter. So the payment there for a year would be 750 times 4. So let's just start out with that. The payment's going to be $3,000 a year. It's growing at 8%, and we're going to leave it in there for 30 years. We didn't have anything at the beginning, so the present value is 0. And we're investing at the end of each quarter, so let's just run that. And now we just run a basic future value with that rate, that number of periods, that payment, that present value, that type. So let's make the payment negative, so the result's positive, about 340,000. Okay, now that was simplistic, remember. Can we make this exactly accurate based on the fact that we're putting the money in quarterly? Yeah, and what's that going to do for us? It's going to grow a little bit more, isn't it? Because I'm actually not waiting till the end of the year and putting $3,000 in. I'm putting $750 in at the end of every 3 months. So what we want to do here is just multiply by 4. Our periods are 30 times 4. I need an equal sign on that. 120 periods, and my payments are now back to just the 750. And my rate, now I'm not going to get 96 million. It's not going to be that much of a difference. So what I have to do is divide my rate by 4 to indicate that we have 4 compounding periods per year. So, whoops, I need to make that an equation. Equals 0.08 divided by 4. And so it's actually going to be a pretty substantial difference from 340,000 to 366, so about $26,000 different if we compound quarterly. And the quarterly rate's going to work out to 2% per quarter or 8% per year. So that's the way we would handle that if it's less than an annual basis for the investments and or the compounding. All right, now we can go back up here and point to part B. Actually, let's do part B for the true amount down here. So paste this down. And part B says, how long will your money last if you start withdrawing $9,000 at the end of every quarter after you retire? Well, I don't know, but Excel does, so all I need to do is run a number of periods function. Returns the number of periods for an investment based on periodic constant payments and constant interest rate. So my rate's going to be the same. We're doing this on a quarterly basis, so I'm going to keep all this new data down here at the quarterly data. The payment now is $9,000. So I'm going to write that in as minus 9,000. The present value, we're going to reduce this. The present value is what we started with here, what the annuity grew to, or the investment grew to, I should say. The future value, we're going to draw it down to 0. And then the type at the end of every quarter, so we're going to keep that at 0 as well. So that tells me it's going to go for almost 85 quarters. Let's make that in years. Let's just divide that by 4 to put it into years. It's going to last me 21 years. So not too bad. $9,000 a quarter. You know what that's divided by 3 months. That's $3,000 a month. And hey, I could live on that if I don't have a mortgage payment or a car payment, which I don't think I will when I'm that old. So there you go. There's a little bit of retirement planning for you. So easy to do in Excel. The hard thing is coming up with a proper interest rate assumption. But once you get that, and the timing, pretty easy. Okay, so 853 is a very similar problem to that. That one's also quarterly, so you're probably going to want to do it the way I did it down here. Divide the rate by 4, multiply the in per by 4, and then deal with your quarterly amounts there. Go ahead and do it that way, and forget about the way I did this up here, because this is just kind of a shortcut because I used the wrong data. Alrighty. 854, we're reaching the end here, folks. 854, this one's a little interesting. I love the Simpsons references throughout this book.
Moe's Tavern, where the elite meet to drink.
Moe says that comes to you for financial advice. He is considering adding video games to his tavern to attract more customers. The company that sells the video games has given Moe a choice of 4 different payment options. Which of the following 4 options would you recommend that Moe choose, and why? And then after all these options, it says Moe tells you can earn 6% annual interest, so that's going to be the discount rate we use for each option. Basically what we want to do is pick the option with the highest present value. Now I'll walk through a couple of these, and then I'll let you do the others on your own. Okay, so Option 1, pay $5,900 cash immediately. Well, that one's easy. We don't even have to discount that, right? Option 2, pay $6,750 cash. Option 2 is going to have a future value of $6,750 in one lump sum 2 years from now. So it's 2 years out. Discount, remember the rate Mo told us which he could get, which is 6%. No payments type, so we can run present value on that. Rate, INPER, payment, FV type. That works out to 6,000. Make the future value negative to make the present value positive. So that's a little bit better. It's about $107 better than option 1. Okay. Option 3, pay $800 at the end of each quarter for 2 years. End of each quarter, so that's 4 periods per year times 2 years. So what's our INPER going to be there? 8, right? 2 times 4. And then what's our rate going to be? It's going to be 6% divided by 4. So you can work that one out. And then option 4, pay $1,000 immediately plus $5,250 in one lump sum. Let me just get you started on that. $5,250 is a lump sum we're going to discount at that rate for over 2 years. And then we're going to add $1,000. So the way I'm going to do this is equals the present value for everything. You know, plug in the numbers and then just add the $1,000 that we get today to the calculation, right? And then see basically which of those has the highest present value, and that's going to be the best option. Okay, last but not least, 55 and 56. And here we're dealing with future value of annuity. Oh no, I'm sorry, it's not future value of annuity. Solving for a loan payment. These are both about the same, so I'll just do one and let you do the other. A55, Titania wants to borrow $225,000 from a mortgage banker to purchase a $300,000 house. The mortgage loan is to be repaid in monthly installments over a 30-year period. That's pretty standard. The annual interest rate is 6%. Let's plug that in. The INPER is, well, 30 years, but we're going to work out monthly payments, so let's multiply that by 12. And let's go ahead and divide our interest rate by 12 while we're at it, because that's how we're going to compound this thing. So that's going to work out to 1%, actually 0.5%. Present value is $225,000. In a loan, that's the principal. It starts with the value and then it amortizes down to nothing, right? That's what amortization means. So we're going to work that out, and now we're going to calculate the payment. Payments are made in arrears, that's right, at the end of the month. And now we can use the equals payment function to work this out. Rate, INPER, PV, FV type. So her mortgage payment is going to be $1,349 a month. We can keep payment negative. Payment's an outflow, so we can write it as a negative number. Okay, 856, very similar setup. It's a 20-year mortgage. So just plug and chug and let Excel do the work for you. Time value of money. Once you get used to it, so easy to do in Excel, and you will become a financial whiz.